Hello, welcome to Joey's Math, AP Precalculus Lesson 1.6, Polynomial Functions and End Behaviors. Today we're going to learn how to describe end behaviors of a polynomial function. So instead of the traditional kind of style of writing end behaviors like this, we're now going to learn something called limit notation. So limit notation is essentially a way of writing end behavior in a more mathematically concise manner. So as the function's input values increase without bound, the output values will either increase or decrease depending on its degree and leading coefficient. This behavior is called the right end behavior and can be written in limit notation as the following. So essentially, as the function goes into the right end side, we can conclude that the function would either go like positive infinity or it would go either negative infinity as the x value goes into positive infinity. So you can represent that as the limit of f of x as x goes into infinity equals infinity, or the limit as f of x goes into the limit of f of x as x goes into infinity equals negative infinity. So you read this limit notation as the limit of f of x as x goes into infinity is infinity. So again, the limit of f of x as x goes into infinity is infinity. So essentially, this notation written in limit notation is equivalent to as x goes to positive infinity, y goes into positive infinity, and this is equivalent to as x goes into positive infinity, y goes into negative infinity. As the input values decrease, meaning that it goes into negative infinity, the function can either increase or decrease as well. If it's this, we can represent that as limit of f of x as x goes into negative infinity is equal to positive infinity, or limit of f of x as x goes into negative infinity is equal to negative infinity. Also, we're going to learn something called leading term test. So if the leading term of an unbounded polynomial is odd and positive, the end behavior is this. So for instance, if let's say we have something called y equals 3x. This is odd and positive, right? So in this case, because the leading coefficient is positive, the end behavior of this odd and positive function would be these, which follows this shape. If the leading coefficient of the unbounded polynomial is odd and negative, like this, the end behavior will follow the shape of this, meaning that as x goes into positive infinity, y will go into negative infinity, and as x goes to negative infinity, y will go into positive infinity. So depending on by looking at the leading term, you can determine the general end behavior of polynomials. Same thing for even degree functions. If the leading term of a polynomial is even and positive, the end behavior will be something like this. If the leading term is even and negative, the end behavior will be a sad face. So it'll be a smiley face if the leading term is positive. It'll be negative. It'll be a sad face if the leading term is negative. I think that's it. Let's just go over one question, and I think that'll be the end of today's video. Okay, example 1. Describe the end behavior of the function f of x equals negative 3x squared plus 5x to the power of 3 plus 4x plus 2. Okay, so if you take a look at this, we have to look at the leading terms. Although this might be tempting, you have to disregard that. You actually have to look at the second term, because if you were to write this in standard form, you have to have 5x to the power of 6 as the first term. If you take a look at the leading term is positive and the exponent is even. Therefore, we can conclude that the end behavior of this function would be similar to something like this. If you were to use limit notation on this, you can write this as limit of f of x as x goes into positive infinity would equal to positive infinity. And the limit of f of x as x goes into negative infinity would be positive infinity. Why? As I told you, because the leading term has a positive leading coefficient as the exponent is even. We can support this conjecture numerically using a scientific calculator. So in order to support this conjecture, we can construct a table. It was I explained this in lesson 1.1. Whenever the question tells you to use function rule to represent something numerically, you have to show a table. So in order to show kind of like the limit or like the unbounded behavior, we could have something like negative like 10,000, negative 100, 0, 100, 10,000. And if you were to use a scientific calculator to calculate those values, I'm just going to do my calculator momentarily. So just bear with me for a moment. We will be getting 5 times 10 to the power of 24. 5 times 10 to the power of 24. 2, 400, we're going to have 5 times 10 to the power of 12. 5 times 10 to the power of 12. These are huge numbers. And as you go that way, it is leading towards infinity. So this table does support the conjecture numerically. So that's all you got to write when you're expected to write the answer. Great. So yeah, I think, yeah, so essentially other questions as well, even if you get like weird numbers, all you got to check is whether the leading coefficient is positive or negative, and whether the leading term's degree is even or odd. If you just know that, no matter how big or tremendous the degree can be, it's super easy to find its end behavior at least. Okay, that's the end of lesson 1.6. Thanks so much for watching. If you have any questions, feel free to email me. Thank you so much.